Thank you so much for the STC to allow me to talk today. My name's David Homfray. I'm the CTO and founder, one of the founders of Space Solar. It's developing a revolutionary new energy system which will deliver baseload energy from space to the Earth using what can be considered just terrestrial photovoltaics. Just to let everybody know, we do accept checks, money and gold bars if you have them available today. Just a little bit about me really quickly. In summary, I've gone from really hard stuff to really easy stuff through my career. I started with human brain mapping. The human brain's really difficult and I couldn't do that anymore. Most complex thing we know in our universe. So I thought I would try and hold a star in a bottle. I spent about 20 years at United Kingdom Atomic Energy Authority. That's also really tricky. So now I'm trying to build the largest structure our species has ever built in space with robots. If you hear anything about what I speak about today, let it be one thing. Net zero and the energy transition, the ability for the UK and nations to have energy security is only about time now. When I started talking about this and started saying, I think we're in a spot of bother, we need to move to energy transition, we had 17,000 days. We now have less than 9,000 days. We have 7 billion people on the planet. 2 billion of those people have no access to electricity. By 2050, there will be 9 billion people. Everything is starting to be electrified. Heating, transport, everything you can think about is being electrified. So I'm using here 50 billion megawatt hours. I expect that to be double, but this is what the the IEA thinks. So only 20% of the energy at the moment is actually what can be considered low carbon. So not only do we need to replace the majority of our current, we also need to increase significantly. It ends up being we need to replace every day for 10,000 days, 5 million megawatt hours per day. So is space-based solar power, and I'll tell you about all of that later, is that the only thing we need? There is no silver bullet. So anybody who tells you that nuclear, renewables, energy storage is the answer, please take with a pinch of salt. In order to meet the energy transition, we would have to build one nuclear power station every week. And they take 20 years to build at the moment. We would need to lay 100 square kilometers every day of PV, or 250 of offshore wind. This cannot be done. We need to do everything. We need to do it now. We need to invest and we need to accelerate the delivery of renewables, the delivery of new nuclear, SMR. We need to make sure that we are more energy efficient and we need to start working on new forms of energy. And so this is the puzzle. If we can meet these 4 factors, we win the game. We need sustainable. We're going to use more and more materials. We're going to mine more materials to meet the energy transition. We really need to notice it. Don't think about it as a moral situation. Think about it as where actually materials are just going to become more expensive. It's a financial and economic decision we're making. Scalable. I've already said it's a time thing. It's about gigawatts per year. Equitable, we need to find the commerciality to allow people to make money, but we also need to think from a global perspective. How do we help the developing nations have energy equity? Because without that, we will continue to have just geopolitical chaos. And finally, reliability. We need to make sure that our manufacturing base, our industry base, and the general public have electricity when it's needed. So, the next thing is, why are we even thinking about things like space-based solar power? Why are we thinking about fusion? Can't we just use everything we've got? We are born to innovate. We are here because we are explorers. We're supposed to find the next thing. That's what we are built for. So whether it's fusion, space-based solar power, our job is to explore and try to create the next generation of products. And these are two quotes from the people that I think absolutely are exemplars of trying to explain why we need to explore and to build the next generation of technology. So, quick, I started my job in fusion. This is the first fusion reactor we know of. It is 99.86% of the mass of the solar system. It cheats when it comes to fusion. Because it's so massive, it is able to confine and contain those particles really easily. We would find it very difficult to build something this big here in the UK. It's also a pretty rubbish fusion reactor. 1 watt per meter cubed. Can you imagine if I was trying to sell that to an investor? So we do it by the triple product. Confinement, density and temperature is a really crude way of saying how good your fusion reactor is. We have to go to higher temperature. This is around 10 million degrees C. I used to work on fusion reactors which were at least 100 to 150 million degrees C. And this was my first machine. This is the Joint European Torus. It's just closed down, and it is, I am unbelievably biased, so everything I say through here, just take into account I'm biased. The finest machine our species has ever built. I was very fortunate to be the engineer in charge of JET for around about 12 years, but it's a science experiment. We were never going to make a product out of this. It taught us about plasma physics, it taught us about the technology, but it didn't tell us what the product looks like. And that's just to show the size. You can see the standard European person. I happened to build quite a lot of reactors in my time, but I want to point down to the bottom left. That is the STEP machine. That is the UK's commercialisation of fusion, and I worked on the original programme of how we would commercialise. So now the question is, why would I go to space-based solar power when I was pretty good at making fusion machines? By the way, that fusion machine there is one I designed for spaceships. Sorry, it doesn't matter. So why space-based solar power? Why would I leave fusion? It was a question my father asked me. I will talk about how space-based solar power works later. But if it would work, it basically takes intermittent technology and it makes it baseload. Doesn't matter about night and day. It doesn't matter about weather. It's dispatchable. One solar power satellite can see a quarter of the globe. So if your wind is doing well, your renewables are doing well, that's no problem. I'll move my beam to Africa or Europe, anywhere, and I can do it in milliseconds. It's scalable because it takes the technology and it moves it more into the field of mobile phones and the automotive industry. It's all about modularization. I can get the learning curves and the economies of scale. When it comes to being equitable, I've already mentioned, I can point anywhere on the globe and deliver power, whether it's the developing nations or the developed nations. It's sustainable because we're closer to the source of fuel. It means that we need less active stuff. And commercial, it would mean from independent sources 143,000 job years over the programme. It has the potential to have a GDP multiplier of 2.8. So every £1 received, we could generate a further £1.80 within the economy. So now I'll come back to this slide. So, was that me? So sustainable. It's sustainable. We've done a study with the University of Strathclyde. They showed this would have a life cycle assessment, a kind of carbon value which was half than terrestrial, and it would use 10% of this equivalent terrestrial solar farm. Scalable, it's all about manufacturing. I should be able to put a nuclear reactor per year up. Equitable, it is seen to be one of the lowest forms of electricity, with current launch $30 per megawatt hour, and if we get to where people believe the launch cost will be, down to $10 per megawatt hour. And reliable, we turn it on just like a nuclear power station. So, sounds really easy. It was first talked about in 1941 by Asimov. NASA proved it by the 1970s this would work. But where it's become economic is due to the cost of launch. The entire capex for this system is all tied into the cost of launch. And so 2 independent studies, one for NASA and one for ESA and one for the UK government, showed that the economics are now there. And just to say, that 1941 comic I managed to get hold of, which is really cool. And Asimov wasn't even famous enough to get onto the front cover. So this is our system. We basically take photovoltaics and we move it into space. The 2 CDs that you see on the top and bottom are reflectors. They always point at the sun. On the top, so you can see a helix in the center, that's our power core. If you were to look from the reflector and look down, you would see a perfect circle of PV. And from the other side, we have 1.5 billion antennas, all working in synchronization to send a beam of microwaves at around 5.8 gigahertz, which is transparent to the atmosphere, to a receiver which looks like a bit like a fishing net on poles. This is an absolute whopper of a spacecraft. From top to bottom it's around 4 kilometers, and in diameter it's about 1.8 kilometers. However, it's unbelievably sparse. So actually the power core only weighs about 350 grams per meter squared. So this is our roadmap. Space Solar started around about 2022. I've been in public sector for my entire life. I had no interest in a startup, but apparently that's what we needed to do. So I became part of a startup. Yay. So we've got a 10-year program within 3 years. So Hawk next year will be a terrestrial demonstrator. It will be around 2 meters of wireless power transmission over around about a kilometer. In 3 years' time, we will deliver 2 space missions. One that will deliver wireless power transmission using the modules that we will iterate over time. And one is where we're going to build a 10-meter structure in space and hang off a big solar panel. So you not only can build space-based solar power, but in orbit data centers, new commercial space stations, the next generation of optical telescopes all could use this backing structure. By 2030, we will take the ability to build a structure and the ability to do wireless power transfer, and we'll put it together. We're going to build a big picture frame around about 80 meters by 80 meters, and then we'll actually stitch a number of these modules together. And then in 10 years' time, we can deliver a 700 megawatt system. And by around about 2 years after that, we want to deliver 2 of those systems within that year. That's how ambitious we can be, but this is not about Space Solar. This is about us all working together to deliver this. Right, so we're not just a paper-based and we're not just doing presentations. We build things every day. That's our job. We build, we learn, lots of things break, lots of things fall apart, and often we have to get a dustpan and brush and put it all back together again. So the Harrier system is the world's first. So that helix that I showed you, this is the world's first demonstration of a 3-dimensional retrodirective phased array. One of the problems with space-based solar power is you have to point at the sun and point at the earth all the time. And unfortunately, they're always blooming moving. So the way that we do it is we always point at the sun, and we use this helix to be able to electronically move the beam. That means we have no moving parts on the system. It means that all the parts are used all the time, drops the mass down, and therefore we get really good economics. And Jaltec were part of the partnership that helped us build this. We then moved on to a £2 million design study. This was from the UK Space Agency in Desnes, where we looked at the final 700 megawatt system, and we delivered basically a solution, a design solution for every single function. So instead of lots of other space-based companies that are looking at the individual component, which is the highest risk, and then hoping to the gods that it fits into a system. We've said, what does the product look like, and what do I need to do today? What do I need to do tomorrow? So we've now associated and designed every part of the subsystem, and what you can see here is the actual blades that will fulfill our power core. From that, we work with MDA in Canada. They're the world's leading robotics specialist. So we've even got to a point now where we know how to build this thing in space. That's a docking hub. Every time you see a little flashing light coming across, that's a new launch. We bring that, and those cubes are around 20 meters by 20 meters. We bring all of the structure by chemical propulsion, so we go as fast as possible. At the same time, we deliver all the rest of the stuff by electric propulsion, and it takes its time. We're in a gravity gradient mode. That means that we're pointing at the Earth at the moment, and that means that we don't need to do so much station keeping. And then basically what we're doing is we're just building cubes. We're just putting cubes together. We've taken up a big bunch of Lego, and we are putting that Lego together. We then put the kind of backing structure on for the reflectors, and the yellow thing going in the center are the two gantry cranes that will run the system. Once we've done that, we actually move it to where it's sun facing, and so when it's actually now sun facing, we now push the system up. So it's able now to get a thermal equilibrium once we put the reflectors in, so we can put the power core. And again, this is all delivered by MDA Canada. They've built Canadarm2 for the International Space Station and the Space Shuttle. We know every time a Firefly goes in, we know what the systems are that are being sent. So now we do this, we're basically in a position, this is going far slower than normal, it's normally far more exciting than this. We now reflect the system, put the reflectors on the system, and then once we've done that, we receive via electric propulsion the power module that built the core. And as I say, it's a bit slower than normal, so hopefully once that's done, we go straight to, and then I can move on. And then we start to build the power core. There we go, that'll do. So to build those cubes, what we need to do is actually take, because of packing density, we take a tube, we flatten it, and then we roll it in a tape. It's really good packing density. So what we've done is this year is we've designed the robots that will actually go and transport around this system, build those cubes. Working alongside the United Kingdom Atomic Energy Authority, we've started to design the initial steps of how you actually build those cubes in space. And actually, we will use these transporters for our year 3 demonstrator. So, oh, I actually didn't switch the thing on in the first place. So, our mission. We're going to build the biggest structure in space, biggest structure in space with robots in 10 years. We will want everybody's participation in this. This is a massive opportunity for the UK to work in a total addressable market of 2.5 trillion a year. It will need gigafactories around the country, and if we can secure UK investment, then this is the place that we can create the next generation of really, really well-paid jobs. This is the sort of sector where your parents, their children, and their children go and work, and we can deliver that together. And I think I'll leave it there. So thank you very much. So I've absolutely cantered through that, and the reason why I've done that, I believe I've cantered through that. I've had no signs or anything. This obviously will be new to a lot of you, so I wanted to give an opportunity of you being able to ask anything. So you might be unbelievably skeptical of this. To be honest, when I first thought this through in 2018, I thought it was absolutely, totally bonkers. I thought it was the most maddest thing I'd ever heard. And I worked in fusion as well. And I still thought it was mad. But when you started getting into the engineering and the mathematics of it, it became more and more sensible over time. And with that cost of that launch cost reduction of around 90%, and because of the reduction in space hardware of around 99%, and because of the ability to build gigafactories and to build things at really high throughput, all of a sudden it became incredibly exciting. Oh, that is very good. So the first question is, how do you deal with space debris and hostile foreign actors? So the space debris side, we are very fortunate because we're actually around 350 grams per meter squared. So if you take a ball bearing and you throw that through a greenhouse, it will shatter and you will get debris. When we have a micrometeorite and a small attack on our system, we will tear. So, but those modules that I was saying about that form the system, they are all independent. So we can lose a large proportion. The beam gets a bit uglier, but technically we can lose quite a large component of that, but still will operate. So what is the orbit, LEO or geostationary? So inverse square law in power, well done. I try to avoid equations on here. So all of our early demonstrators and products are all in LEO to start with. What that means is we don't need such big versions of it. But what it does mean is it zips around the Earth, so there's only a minimum contact time to a ground station. It's a balance between how much you want to ask for what you're delivering. So we start in LEO, but our 700 megawatt version will be in a geosynchronous orbit. That geosynchronous orbit means that we have to be very large because the transmitter diameter, the receiver diameter, the distance between them and the frequency of the microwaves are all related. So the further you are away, the larger you have with a transmitter. Are there competitors? Yes, so it's first of all, space-based solar power is in the Japanese constitution or whatever their version of it is. South Korea, and they launch a satellite next year. Caltech launched a satellite last year. Etherflux, which is an American Silicon Valley, very exciting. They're all very rad and they all wear shorts and t-shirts. They've just received $65 million seed round. As I said, the Japanese launch next year, and South Korea are working on a system at the moment. There are a number of companies. I'd like to think that no. I'm not being biased here. The UK is the best place at the moment for space-based solar power to be developed. In our Cassidy project, we work with 22 separate organisations. Not recommended working with so many partners on a project, by the way. If anyone ever thinks about doing it, it's madness. However, what it means is they all now know about space-based solar power. They know what we want to do. And when we kick off that work, we talk to our gel techs, we talk to our partners and say, we're on the road. So it's really important. So there are many, and again, I think we're going to be in a race with the Chinese. They've made a massive announcement with several billion into space-based solar power. So how far the Earth will panel orbits, already mentioned, Geo. Your last action was go to the pub. Which pubs are we going to? So that's the beauty of space-based solar power. There is enough work to keep all pubs going forever. And then, do we have any? Do you have a grid? Yes. a grid connection solution for the power to be converted back onto the power network? That's a really good question. So in the UK, these receivers are really big. So they're kilometres in size. They're actually only 40% of that of a solar farm, and they're only 8% of a wind farm. So although they're large, they're smaller than normal intermittents. Because they're on a pole, we expect to be able to grow arable crops or have, for instance, terrestrial solar underneath them. So during the day when the sun's going, we will sell our power somewhere else. And it's during the transition of the dusk, we can deliver power. In the UK, to start with, we will connect offshore. We'll connect directly to some of the energy islands that are being delivered now for offshore wind. And when that fishing net are little antennas in the crosses of the fishing net. They go through it's just really a Schottky diode to take AC to move to DC. And then the beauty of it is then we can just use terrestrial solar technologies straight off the shelf. We don't need anything different. We're collecting cells, we're putting cells together, and then we're connecting to the grid. So that's a really beautiful side. The rectenna and the receiver side is the cheaper part. The actual power supply, expensive, can be bought by developed nations. And then the cheap section, which is the receiver, can be delivered really economically to the point that's needed in the developing nations to give them real energy equity. And I can't say how important for that is for geopolitics to have true energy equity. I'm just going to keep asking questions until someone pulls me off stage. Yes, so we're talking about the robotic construction. So can the robotic construction be used anywhere else in space? I don't know who asked that question and if was that the right sort of... So we're looking to deploy both the structure and the robotics to be able to build any structures in space, because we will have a selection of 20 meter by 20 meter cubes, 6 meter by 6 meter cubes, and 2 meters by 2 meter cubes. And the transporters we want to get to are cheap, so they're below around about $1,000 per unit. There is no reason why you can't have really efficient packing density of both the structure and the robots. So send those up first, build the next commercial space station, which can then accept the habitats and all the things that you need. We will have our own patented PV technology we can use to then provide those systems, whether it's the next generation of telescope, whether it's the next in-orbit data center, which is sounding like it will become more important. We can power those things as well as build the infrastructure. Competitors. If I stood under the receiver, would I feel a gentle warming effect? So, interestingly, when we first tried to discuss what our company name should be, my wife did say, why don't you call it, it's definitely not the Death Star. While no ideas are a bad idea, we put it up right in the corner of the thought board. So the microwave beam's around 230 watts per meter squared. 2 minutes, thank you very much. It's around 230 watts per meter squared. That's around about a quarter of the midday sun. So we have already regulation in place called the ICNIRP limit, which set out how much radiation from electromagnetic waves is allowed to be taken by both workers and the general public. So we will perimeter off those receivers. However, it would be a really awful weapon. Any weapon that would cost several £billion and you can resolve by putting UV 50 factor sun cream is not the most efficient of weapons. So yes, you could sit under there. You wouldn't want to sit under there for a long time, and the ICNIRP regulations would really not like you to do it, but yes, you could. And I think I've probably got time for one more question. We've already talked about the energy beam. how confident are you achieving the buy-in from the UK market, red tape, etc.? So I'll talk about this from two perspectives. So first of all, let's talk from a regulatory point of view. I think you said 2 minutes before, didn't you? Oh, it's now 1 minute. So from a regulatory point of view, I would actually suggest that the UK is probably the best place to do this in, because we actually have quite an innovative regulatory environment. I've experienced that both in the fusion world, where we've talked to the Office for Nuclear Regulation and HSE, and within 9 months put out a green paper. And already we have a regulatory working group with government on board with the CAA to talk about, can we secure frequencies, can we secure areas offshore. So from a regulatory standpoint, I think we're in a really good place. The red tape on leveraging finance versus private finance is a different situation. I think that the UK is not really well placed to help. We have some of the cleverest people on the planet in the UK. I would ask a question: why are we not one of the most prosperous countries in the world if we have the most cleverest people? I would say that taking innovation and making a product which is a combination of having clever people, private finance and government support is not quite there at the moment. So I know this was red tape regulation, but I thought I would just throw that in as well. And I think I will finish now, because there's a thumbs up, so I will definitely finish. Well, thank you so much.